Semigroups and their representations, Lecture 6, Regular semigroups. Let us start with the definition of a regular element. Our setup, let S be a semigroup. Definition: an element A in S is called regular, provided that there exists an element B in S such that ABA is equal to A. Example 1. Any idempotent E in S is regular because E times E times E is equal to E. So we can take as the element B the element E. Example 2. The additive semigroup of all positive integers has no regular elements at all, since for any positive integers A and B, A plus B plus A is strictly greater than A. Example 3. Every element in the transformation semigroup Tn is regular. Indeed, take some I in the image of an element alpha in Tn. For this I, choose some mi such that alpha sends mi to I. And let beta be some element in Tn, not necessarily uniquely defined, such that beta sends I back to mi for any element I in the image of alpha. It doesn't matter how B operates on the elements outside the image of alpha. Then, directly from the definitions, we have that alpha after beta after alpha is equal to alpha, and this means that alpha is a regular element. Now we can define the notion of a regular semigroup. Definition: a semigroup S is called regular, provided that every element of S is regular. For example, on the previous slide we have proved that the semigroup Tn, the full transformation semigroup on the set 1, 2, and so on up to n, is regular. Example 2. At the same time, we also saw on the previous slide that the additive semigroup of all positive integers is not regular. Example 3. Every group is a regular semigroup. Indeed, if G is a group and A is an element in G, then A times A inverse times A is equal to A. So A is indeed a regular element. Example 4. If A is a non-empty alphabet, then the semigroup of all words over A is not regular. Indeed, for any non-empty word U and any word V, the length of the word UVU is strictly greater than the length of the word U, and hence UVU cannot be equal to U. So any non-empty word in this semigroup is not a regular element. Next, let us look at more structure which is given if we have regular elements in the semigroup. So let S be a semigroup and let A be a regular element in S. Let B be some element in S such that ABA is equal to A. Our first observation is that the element AB is an idempotent, which is right equivalent to A. Proof: if we multiply the identity ABA is equal to A with B on the right, we get AB is equal to AB. So AB is indeed an idempotent. Also, AB is equal to A times B, and A is equal to AB times A, which means that AB and A are right equivalent. Similarly, the element BA is an idempotent which is left equivalent to A, and the proof is similar to the proof of the first observation. So if we have a regular element in some semigroup, then we have certain idempotents. So there is an idempotent which is right equivalent to each regular element, and there is an idempotent which is left equivalent to each regular element. Now let's look closer at the right and left cells of idempotents in a semigroup. Recall that the set of all idempotents of the semigroup S is denoted by E of S. Lemma: let S be a semigroup and E an idempotent in S. If A is an element in S which is either right or left equivalent to E, then A is a regular element. So any element which belongs either to the right class or to the left class of some idempotent is a regular element. Proof. Assume that A is right equivalent to E. The case when A is left equivalent to E is similar. Then there exist x and y in S such that AX is equal to E and EY is equal to A. Note that E times E is equal to E is an idempotent, and this implies that E times A, which is equal to E times EY, so EY is A, E square is the identity, so this is equal to EY, which is equal to A. So E times A is equal to A. And from this, we deduce that AXA is equal to E times A because E is equal to AX, and EA is equal to A, so this is equal to A. So AXA is equal to A, so A is a regular element. As a corollary, if A is a regular element of some semigroup S, then any element B in S, which is either right or left equivalent to A, is also regular. Consequently, any B in S which is D equivalent to a regular element is also regular. Proof: the right class of a regular element contains an idempotent, as we have seen, and then every element of that class is a regular element by the lemma on this slide. So this implies the claim of the corollary. Now we can define the notion of a regular D class. So we have a consequence. If some D class D of a semigroup S contains an idempotent, then every L class and every R class inside this D class D contains an idempotent. Proof: if E is an idempotent of some D class D, then all elements in the right class of E are regular. Each left class in D intersects the right class of E and hence contains a regular element, and hence it contains an idempotent. So similarly for R classes. So if we have a D class which contains an idempotent, then any left and any right class inside this D class contains an idempotent. And the D class of a semigroup S is called regular if it contains an idempotent. And we can now say that a D class is regular if and only if each element of this D class is regular. A little bit about terminology. Let S be a semigroup and A regular element in S. Definition: an element B in S such that ABA is equal to A is called the pseudo-inverse of A. Another definition: an element B in S such that ABA is equal to A and at the same time BAB is equal to B is called an inverse of A. A remark: this terminology inverse is very unfortunate and confusing because it is very similar to the terminology of an inverse element in the group. It would be better for semigroups to use a generalized inverse or something, but unfortunately the terminology inverse is by now standard, so we will use it. Remark 2. Each regular element has at least one inverse, but usually more than one. So let's show that each regular element has at least one inverse. So if A is a regular element and ABA is equal to A, then we can take the idempotent E equal to AB. So that's an idempotent, so E squared is equal to E. And we also saw that EA is equal to A for this E. And then A times BE times A is equal to ABEA. EA collapses to A, so we get ABA, which is equal to A. So BE is a pseudo-inverse of A. At the same time, BE times A times BE is equal to BEA, BAB. Then EA is A, so this is BABAB. ABA is A, so this is BAB, but this is BE. So which means that A is also a pseudo-inverse to BE. So BE is indeed an inverse of A. Let's look at an example in which we will see that the inverse is usually not unique. Let alpha be an element in the full transformation semigroup Tn. For each element I in the image of alpha, choose some mi such that alpha sends mi to I. And of course note that in most cases this mi is not unique, so we have many choices here how to choose mi. Let beta be a transformation which sends I back to mi for each I in the image of alpha, and additionally the rank of beta is equal to the rank of alpha. And the latter means that the image of beta coincides with the set of our mi's. So outside the image of alpha, we can define beta arbitrarily with one caveat that all those elements should be sent to some of these mi's. So to form such beta, we arbitrarily send the elements outside image of alpha to these mi's. And directly from the construction, we will get that alpha after beta after alpha is alpha, and beta after beta is beta. So any such beta is an inverse to alpha, and unless alpha is an invertible element, this inverse beta is not unique, as we see from the construction. Now we can characterize regular D classes. Theorem: a D class D of a finite semigroup S is regular if and only if there exist A and B in this D class D such that their product AB belongs to D. Proof: if D is regular, then it contains an idempotent E, and we can take as A and B this element E, and then E times E is E belongs to D. Conversely, assume that we have a D class D and two elements A and B in this D class, such that their product belongs to this D class. Since S is finite, we know that the Green's relations D and J coincide, and so there exist elements X and Y in S such that X times AB times Y is equal to A. So A and AB belong to the same two-sided ideal. But then we can iterate this, so for any positive integer I, x to the power I times A times by to the power I is equal to A. If we look at the set of all by to the power I, where I is a positive integer, this is obviously a subsemigroup of S, and it is finite since S is. And since it's finite, it contains an idempotent E. So there is a positive integer I0 such that by to the power I0 is an idempotent. We denote it by E. And it remains to argue that this idempotent E belongs to our D class D. And for this we know that our E, by construction, belongs to the two-sided ideal generated by B. So our E is of the form by to some power, so B is inside this expression. So E belongs to the two-sided ideal generated by B, so E is J less than or equal to B. Also, we know that some expression where in the middle we have A, and then E on the right and then something on the left is equal to A. And this means that A belongs to the two-sided ideal generated by E. So A is J less than or equal to E. But since in our finite semigroup D is equal to J, A and B are D equivalent by definition, so they are J equivalent. So it follows that A, which is less than or equal to E and less than or equal to B, A is also equal to B. So all these three elements, A, E, and B, are J equivalent, and so our D class D contains an idempotent and hence is regular. Let us note that the elements X and Y, which we used in the proof, they do not have to belong to our D class D in general. For example, for the semigroup Tn, for any pair U and V of D equivalent elements, we can always choose an invertible element X and some Y, so this Y doesn't have to be invertible, but in many cases it also can be invertible, such that X Uy is equal to V. Now let us talk about a very specific class of regular semigroups, which are called bands. Definition: a semigroup S is called a band, provided that each element of S is an idempotent. In other words, S is equal to E of S. Remark, any band is obviously a regular semigroup because it consists of idempotents. Every D-class consists of idempotents, so is a regular D-class. For example, for any set X, the set of all subsets of X with respect to the set union is a semigroup and is a band, because any set is an idempotent with respect to this operation. Example 2, if we take any set X, and then the set of all subsets of X, and as the operation the set intersection, we again get a band. And example 3, that's a construction of a so-called rectangular band. Let I and j be two non-empty sets, and consider the set I times j, the Cartesian product of I and j. For two elements I, j and I prime, j prime in this Cartesian product, set that the product of I, j with I prime, j prime is equal to I, j prime. So the left component comes from the left factor and the right component from the right factor. This turns the Cartesian product of I and j into a semigroup and even a band. And this is what is called the rectangular band. Rectangular band can be characterized in a very neat way. Theorem: let S be a band such that x times y times x is equal to x for all x, y in S. Then S is a rectangular band. Remark, let us note that in any rectangular band, x, y, x is equal to x for any x and y in S. So rectangular bands can be characterized by such an identity, and of course band itself is characterized by the identities that x squared is equal to x for any x. Proof. From the identity x, y, x is equal to x, we have that x is j less than or equal to y for any x, y in S. In particular, S has a unique j class. As S is a band, it's obviously periodic. Each element generates a one-element subsemigroup, and so S has a unique D class because D and J coincide. Each H class of S contains an idempotent and hence is a group. On the other hand, each of these groups consists of idempotents and hence is a singleton. So each H class is a singleton. So we have one D class, and we have R classes there, and L classes there, and each intersection is one element. So let I be an L class in S, and let J be an R class in S. Let E be the intersection, that's an idempotent, and then we know that the two-sided ideal generated by E is the whole semigroup. For any element x in S, we have that xe is of course left less than or equal to E, but at the same time E is equal to exe, so E is left less than or equal to xe, and so I is actually the left ideal generated by E. Similarly, J is the right ideal generated by E, and so S, which is equal to SES, and which is equal to SE times ES, is equal to I times J. And now for any element little I in capital I and little j in capital J, similarly to the above, we have that ij is right equivalent to I and ij is left equivalent to j. And so ij is exactly the intersection of the right ideal generated by I and the left ideal generated by j. And so from the egg box diagram, we see that the map from I times j to S, which send the pair I, j to the product ij, is bijective. And directly from the construction, it follows that this map is also a homomorphism of semigroups, and hence it's an isomorphism from the rectangular band I times j to S. And this completes the proof. Next, let us talk about commutative bands. For this, recall that a partially ordered set Q with some partial order less than or equal to is called a lower semilattice, or alternatively a mid-semilattice, provided that for any pair of elements x, y, and q, the set of all elements z which are less than or equal to x and less than or equal to y has a unique maximal element, which is usually called the meet of x and y and denoted x wedge y. For example, for any set M, the Boolean of M is a lower semilattice with respect to inclusions, and the meet of two subsets x and y of M is just the intersection of these two subsets. Also, directly from the definition, we see that the meet of x and y is equal to the meet of y and x, so taking the meet is a commutative operation. And it's very easy to see that it's also associative. The meet of x with the meet of y and z is equal to the meet of x and y with z. So given a lower semilattice Q, the meet operation turns this lower semilattice into a commutative band. Of course, the meet of x and x is x. Conversely, any commutative band S is a lower semilattice with respect to the partial order defined as follows. X is less than or equal to y if and only if xy is equal to x. We will prove it on the next slide. So from this point of view, commutative bands are exactly the same thing as lower semilattices. So now let's prove the claim that any commutative band is a lower semilattice with respect to the partial order defined by x is less than or equal to y if and only if xy is equal to x. Proof. So let S be a commutative band. So we have defined our partial order. Note that xy is equal to yx is equal to x if x is less than or equal to y, and if y is less than or equal to z, then yz is equal to zy is equal to y. But then x times z is equal to xy times z. That's because x is xy. But now yz is y, so this is equal to xy, and xy is x. So this implies that x is less than or equal to z. So our relation is transitive. And of course it's antisymmetric, so if x is less than or equal to y and y is less than or equal to x, then x is equal to y, directly from the definition. And this proves that our relation is indeed a partial order. Now that we have a lower semilattice, if x and y are two elements in S, then xyx is equal to xy because it's commutative band. We can move x past y and then x squared is x. And similarly, xyy is equal to xy. So xy is definitely less than or equal to both x and y. Also, if we have an element z such that zx is equal to z and zy is equal to z, then zxy is equal to zy is equal to z, and so z is less than or equal to xy, which means that xy is indeed the meet of x and y. And this completes the proof of the lemma. Finally, let us discuss zero-simple semigroups. Definition: a semigroup S is called simple provided that it doesn't have any ideals different from S. For example, any group is a simple semigroup, or any rectangular band is a simple semigroup. Definition: a semigroup S is called zero-simple provided that it contains a zero element and the only ideals of S are S and 0. For example, the multiplicative semigroup of 0 and 1 is zero-simple. Example 2, for any non-empty set X, the semigroup of all partial injective transformations of X of rank at most 1 is zero-simple. So here the 0 element is the unique transformation of rank 0, the transformation with the empty domain. Next, let us give a construction of what is known as Rees-metric semigroups. So let I and j be two non-empty sets, let G be a group, and let C be a map from J times I to G, disjoint union with the 0 element 0. Consider the set denoted M of I, J, G, and C, which consists of the 0 element, and all elements of the form I, G, J, where I is in I, J is in J, and G is an element in our group. So we now want to define on this set the structure of the semigroup. So 0 is of course defined as the 0 element of this semigroup. And how do we multiply our I, G, J? So if we have I, G, J and I prime, G prime, J prime in our set, we define their product as follows. So we look at the value of our map C at J, I prime. If this value is 0, then the product is 0. If this value is non-zero, then the product is the element I, G, C of J, I prime, G prime, J prime. That's the formula. And the claim is that this turns our set into a semigroup. Let's prove this. We will think about our element I, G, J as an I times J matrix, so the matrix whose rows are indexed by I and columns are indexed by J. Almost all entries in this matrix are 0, except for one, and that the ij's entry, so the entry in row I and column J, and that entry is equal to our G. Of course, we think of the 0 element as the matrix where all entries are 0, and this is I times J matrix. And we think of our map C as a J times I matrix in the obvious way. So in the row J and column I, we have the value C of J, I. Then the product of I, G, J with I prime, G prime, J prime is simply given by the matrix product of this element, of the matrix of the first element, times the matrix of C, times the matrix of the second element. And this is of course associative, as matrix multiplication is associative. So the semigroup which we obtain in this way, the semigroup M of I, J, G, and C, is called the Riesz matrix semigroup, which corresponds to our datum. Now we can use this to classify regular finite zero-simple semigroups. Theorem: let S be a regular finite zero-simple semigroup. Then S is isomorphic to a Riesz matrix semigroup for some finite I, J, G, and some C, which satisfies the conditions that every row and every column of the matrix C contains a non-zero entry. Conversely, each such Riesz matrix semigroup is a regular finite zero-simple semigroup. So regular finite zero-simple semigroups are exactly the Riesz matrix semigroups with one condition on the map C, so the matrix C should have a non-zero element in each row and in each column. Proof. To prove the second claim, we need to show that the ideal generated by each element I, G, J in the Riesz matrix semigroup is the whole Riesz matrix semigroup. And for this, we need to solve the equation. We start with our element, we multiply with some x on the left, we multiply with some y on the right, and we need to get any I prime, G prime, J prime. To solve this equation, as the left element x, we take I prime, A, J2 prime, such that C, evaluated at J2 prime, I is non-zero. And this exists by our assumption on C. For y, we take the element I2 prime, B, J prime, such that C of J, I2 prime is non-zero, which again exists by our assumption on C. And now it remains to adjust A and B such that A times the value of C at J2 prime I times G times the value of C at J I2 prime times B is equal to G prime. And this is clearly possible since G is a group. This solves our equation and implies that the Riesz matrix semigroup, with our assumption on C, has only two ideals, the zero and the whole semigroup. Also, if the value of C at some pair J, I is non-zero, then the element I, C of J, I inverse, J, is an idempotent. It's a straightforward computation. And hence, our semigroup is regular because it contains a non-zero idempotent and it only has two D classes. And this proves the second statement. To prove the first statement, let S be a finite regular non-singleton zero-simple semigroup. It's regular, so we can take a non-zero idempotent of S. Let's define G as the H class of this idempotent. Define I as a set of all non-zero R classes in S, and define J as a set of all non-zero left classes in S. For each right class I, pick some element AI in the intersection of I with the left class of E, and for each left class J, pick some Bj in the intersection of J with the right class of E. This should be E, not A. Now for a right class I and the left class J, sending a group element G to AIGBJ is a bijection from G to the intersection of I and J. Also, for a left class J and the right class I, the product BJAI is either 0 or belongs to G, because Bj belongs to the right class of E and AI belongs to the left class of E. So it makes sense to define the value of our map C on the pair J, I as BJAI. And then directly from the construction, it is easy to see that the map from the Riesz matrix semigroup to S, sending I, G, J to AIGBJ is an isomorphism. So this completes the proof. Some additional problems and questions at the end. Problem question 1. Determine the number of inverses in Tn for a rank 1 transformation. Problem question 2. Prove with all details that in the semigroup Tn, for any pair U and V of D-equivalent elements, we can always find an invertible x and some y such that xuy is equal to V. Problem question 3. In the characterization of rectangular bands, check that the map from I cross J to S, which sends the pair I, J to the product of I and J, is a homomorphism from the rectangular band I times J to S. Problem 4. Check the associativity for the meet operation for any lower semilattice. And problem question 5. Complete with all details the proof of the last theorem, and additionally establish a sufficient and necessary condition for two Riesz matrix semigroups to be isomorphic. Thank you very much, and see you next time.